Alright, hey everybody. So this will be a quick video on function composition, and also briefly we'll talk about just some operations on functions. So first of all, consider two functions, f and g. So f of x is 2x plus 3, g of x is x squared plus 1. So as far as function operations go, it's pretty straightforward. So the big kind of idea is that polynomials, they operate a lot like numbers do. It's kind of a cool thing. So in particular, we can operate on them the same way that we operate on numbers, adding them together. So this notation right here is f plus g of x. This is the same as f of x plus g of x. What's the difference between these two notations? Well, in this first notation, you're essentially taking f plus g to be a new function. F plus g is a function. You could call it like h of x. But f plus g of x is the same as f of x plus g of x, which is quite literally just like the straightforward f of x. So 2x plus 3 plus g of x, x squared plus 1. So we're rewriting it, making it a little bit cleaner. Let's see, it's going to be x squared plus 2x plus 4. This is f plus g of x. If you were to do f minus g of x, it's the same thing. Just be careful of the parentheses. So f minus g of x is the same as f of x minus g of x, which is, again, and it's a smart idea to put the functions in parentheses, especially this second one, g of x, because this minus sign is going to be distributed to both the x squared and the positive 1. So I can see where a common mistake might be to not put those parentheses in, and then you write it as 2x plus 3 minus x squared plus 1. Which is wrong, because this negative needs to be distributed, which means that when we distribute the negative, so we get negative x squared plus 2x, then here we would have 3 minus 1. 3 minus 1 is 2. So that's f minus g of x. If you wanted to do f times g of x, written as fg of x, this is the same as f of x times g of x. So 2x plus 3 times x squared plus 1. And remember, when you have something like this, two binomials, you have to FOIL them out. So this will become 2x cubed plus 2x plus 3x squared plus 3. There's really no more simplifying to go on there. You could rearrange it as 2x cubed plus 3x squared plus 2x plus 3. And then finally, f over g of x, f divided by g of x, well, it's going to be exactly what you're expecting at this point, assuming that g of x is not the zero polynomial, is not just 0. This is possible. So, and it's, yeah, nice and straightforward. F of x, 2x plus 3 over x squared plus 1. Very straightforward, those operations are. Maybe a little bit more confusing for people is something called function composition, which is taking one function and using it as input for another function. And here's the notation. F, this is like a little circle, G, kind of like the degree sign, but it's sort of like in the middle rather than like sort of used as like in the place of where like an exponent would be. F of G, that's how you read this, f of G of x. And this is defined as f taking g of x as an input. So one thing to be aware of here is that this notation, function composition, things are sort of absorbed from the right. X gets absorbed into g, g of x gets absorbed into f. And this is literally the same as taking g of x, x squared plus 1, and plugging that in into f of x wherever you see x. So f of x is 2 times x plus 3, but in place of x, we're plugging in g of x. So 2 times x squared plus 1 plus 3, right? We're just taking x squared plus 1 and plugging it into x. 2 times x squared plus 1 plus 3. Distribute the 2. 2x squared plus 2 plus 3 is 2x squared plus 5. So this is f of g of x. We can also talk about g of f of x. And of course, we could have done all of the same things up here. Multiplication and addition are commutative. So if you did g plus f of x, you would get the exact same thing. If you did gf of x, you would also get this same product. And same thing with the subtraction and the division. Those are not commutative though. So g minus f of x is going to be different than f minus g. G over f of x is different from f over g, but it's like the exact same idea. G of f of x is the same idea as the function composition, the f of g of x, but like I said, remember, everything gets absorbed from right to left. So this is the same as g taking f of x as an input. So x gets put into f of x gets put into g. So this would be the same as taking g of x, which is x squared plus 1, but instead of x, we're plugging in f of x. So 2x plus 3 squared plus 1, g of f of x. And FOIL this thing out, it'll be 4x squared plus 12x plus 9 plus 1. So 4x squared plus 12x plus 10 is function composition. Let's see, what else should I say? Right, so common misunderstanding, there is a big difference between function multiplication, and function composition. They somehow look or feel similar, but they're completely different operations. So don't get them confused. Let's see, the very last thing, maybe I'll do like an example, because sometimes you might be given sort of tables and asked to do some function composition. So let's see here, not using the same f and g, maybe I should just give them different names to distinguish. So we'll have some x, and then we have some h of x, and I don't know what the heck, let's get crazy, alpha of x. Wow. Yeah, alpha of x, it's just a function. And suppose that we have the x values 1, 2, 3, 4, 5, 6. So we're just like I'm just listing off a table. This is like, imagine that there are two functions, h and alpha, that are defined on 1 through 6. H of 1 is 2, h of 2 is 4, 6, 8, 10, 12. So it looks like h of x is just 2x, and then maybe alpha of x is just some strange, unordinary function. -1. I'm just coming up with, I have like these written down, so it's an example that I did previously. So suppose that we're given this sort of table like this, and then maybe we're asked to make some calculations. Maybe we're asked to do something like h of alpha of 1, right? Function composition, but this time we're not given any polynomials or functions. We're not given the formula of the functions. We're just given some set of outputs. Which, by the way, maybe I should say, like with this function composition and all of these operations, once you've kind of found this end function, if we were asked, say, to find f over g of 2, then once you have this sort of formulation, it just amounts to plugging in 2 into the end function. And that's essentially what we're going to do over here, just we're not given the formulas. So what we have to do, you work from the inside out. So h of alpha of 1, first we need to determine what is alpha of 1. Well, alpha of 1 is 3. So this is the same as h of 3. What is h of 3? h of 3 is 6. So h of alpha of 1 is 6. By the way, this could also be written as h of alpha of 1. Right? So these are the exact same things, just like we did over here. These are the exact same the exact same function. It's just sort of written differently. Let's see, one more example. Maybe we'll switch it up. We'll do alpha of h of 3. All right, again, we're working from the inside out. So first we need to determine what is h of 3. H of 3, if we plug 3 into h is, oh right, we just found that. H of 3 is 6. So this becomes alpha of 6. What is alpha of 6? It's 9. Alpha of 6 is 9. So this is, and again, this is the same as alpha of h of 3 equals 9. So it might be helpful for me. I tend to, like, if I'm given this kind of notation, if I'm asked what is alpha of h of 3, for me, I rewrite it this way because it sort of is more obvious to me how everything works. But the idea, again, is things get absorbed from right to left. So this 3 gets absorbed into h first, then h of 3 gets absorbed into alpha. Right, is there anything else I should say about that? No, I don't think so. The only other thing that might come up for you is trying to figure out the domain of a composite function. There are ways, without actually like writing out the composite function all the way, like what the actual composite function would be. There are ways, methods of determining what the domain of the composite function would be, just sort of looking at the two individual functions. Me personally, I think it's a lot easier, less complicated, to just write out what the formula is, assuming that you're able to, and then write the domain from there. Otherwise, the idea would be to consider the domain of the internal function, then consider the range of the internal function, consider the domain of the outer function, and see where the range and the range of the inner function and the domain of the outer function, see where they match up. And then from that set, remove any of the problem points of the internal function. So yeah, it's a little bit more complicated doing it that way. I think if you can just write out the formula, it comes together a lot cleaner. All right, let me know if you have any questions.